The USS Gerald R. Ford, the most advanced aircraft carrier in the United States Navy, is an impressive demonstration of naval engineering and technology. Its monumental size and ability to operate in complex scenarios make it a modern marvel. However, a common question arises: how does such a colossal vessel, made of tons of steel and with a seemingly disproportionate structure, manage to float and remain stable? At first glance, the design of the Gerald R. Ford, with its apparently smaller base compared to its enormous superstructure, might seem vulnerable to tipping or instability at sea. The explanation for this phenomenon lies in the laws of physics, specifically Archimedes' principle, a concept used since antiquity to explain the buoyancy of objects. According to this principle, any object submerged in a fluid displaces a volume of liquid whose weight equals the buoyant force acting on it. Simply put, an object floats if the buoyant force pushing it upward is greater than the gravitational force pulling it downward. In the case of an aircraft carrier, even though it is made of steel, its average density is significantly reduced by the large number of hollow spaces in its structure, allowing it to displace enough water to stay afloat. To put this in perspective, the USS Gerald R. Ford has a displacement of about 100,000 tons, meaning it displaces approximately 100,000 tons of water when in operation. This is equivalent to approximately 96 million liters of water. Its average density is considerably less than that of water, ensuring it remains afloat. But floating is not the only challenge. For a vessel of its size, maintaining stability, even under extreme conditions, is crucial for functionality and safety. The stability of a ship like the Gerald R. Ford is intrinsically linked to the concept of the metacenter, a critical point in naval engineering. The metacenter is the point where the buoyant forces are concentrated when the ship tilts to one side. The greater the distance between the metacenter and the ship's center of gravity, the greater its stability. For aircraft carriers, this distance must be carefully calculated to prevent the ship from capsizing in adverse situations, such as storms or sharp maneuvers. Designers use advanced calculations to position the center of gravity strategically, usually below the metacenter, ensuring the ship returns to its original position even after significant tilts. Additionally, weight distribution on an aircraft carrier is another critical factor. The Gerald R. Ford carries aircraft, fuel, ammunition, equipment, and a crew of thousands. All this must be carefully distributed to prevent weight from concentrating at a single point, which could compromise stability. For this, advanced load and ballast management systems are employed. These systems allow operators to adjust weight distribution in real time, moving water between internal tanks to balance the ship. Another fascinating aspect of the Gerald R. Ford is its resistance to external impacts. As one of the most advanced aircraft carriers in the world, it is designed to withstand extreme conditions, including explosions near its structure. In 2021, the ship underwent an impact test known as shock trials. During this test, high-power explosives, equivalent to about 18 tons of TNT, were detonated near the ship. These tests simulate wartime conditions and assess the carrier's ability to withstand underwater explosions and other impacts. The Gerald R. Ford passed these tests successfully, proving its robustness and the effectiveness of its design. Turning tests are another essential part of an aircraft carrier's performance evaluation. These tests involve high-speed maneuvers where the ship is forced to make sharp turns to assess its responsiveness and stability. Despite its gigantic size, the Gerald R. Ford is incredibly agile in these maneuvers, thanks to advanced propulsion and steering technologies. These tests ensure the ship can operate in combat situations where quick changes in direction and speed are crucial. In addition to its ability to float and remain stable, the Gerald R. Ford is also equipped with cutting-edge technological systems that set it apart from its predecessors. Among these innovations is the Electromagnetic Aircraft Launch System (EMALS), which uses electromagnetic technology to launch aircraft more efficiently and with less wear compared to traditional steam catapult systems. This not only increases the carrier's operational capacity, but also reduces maintenance needs, prolonging its service life. Another technological highlight is the dual-band radar system, which offers greater precision in threat detection and navigation. This system is complemented by advanced defenses against aerial and submarine attacks, making the Gerald R. Ford a floating fortress. However, even with all this state-of-the-art technology, the ship's safety still depends on careful planning and the expertise of its crew. History has shown that neglect in maintenance or planning can lead to tragedies. A notable example was the sinking of the Sewol ferry in South Korea in 2014.